Hi there guys, how's it going? Mike coming back at you with another video on Foundations of Math 2. In the previous video, we looked at truth tables and how we use truth tables to determine when logical forms can be true or false based on the truth values of the components of the logical form. In this video, we are going to continue on with using truth tables, but we're going to talk about some other terms in the world of logic. So let's get right into it. Sometimes a logical statement or a logical form is always true regardless of the truth values of the components, or it's always false regardless of the truth values of the components. If we have a statement that is always true no matter what the truth values of the components are, that logical statement or the logical form is called a tautology. If we have a logical form that is always false, regardless of the combinations of truth values of its components, that logical statement or form is referred to as a contradiction. And we check for tautologies or contradictions by using truth tables. If in that final column where we have the truth values for the given logical form, if every value in that column is a t, then you have a tautology. If every truth value in that final column is an f, then you have a contradiction. So here's an example. We're going to show that P and not P is a contradiction. Now, just on the sound of it, saying something and the opposite of that same thing just doesn't sound like that should happen. And that's true. But let's actually see it using truth tables. So I only have a P involved in here in some way, shape, or form. I actually have redundant rows here. So let's check it twice. We have P as true, true, false, false. And then not P, we have false, true, false, false, true, true. So then let's fill in the columns for P and not P. A true and a false gives me a false. False and a false. A true and a false gives me a false. A false and a true gives me a false. And a false and a true gives me a false. So clearly we see no matter what that P and not P, no matter whether P is true or P is false, we're going to find that P and not P is always false. So this is an example of a contradiction. And like I said, if you weren't sure the first time, we just checked it a second time because why not? There we see our completed truth table. I'll let you verify on your own. So check this guy. Check that P or not P is a tautology. I'll let you verify that guy on your own. It's going to be very similar to the truth table that we did here, but you should find that every value in this final column here will be a T instead of an F. Sometimes logical statements or logical forms have the same truth values for every possible combination of truth values of the components. When this happens, we say that the statements are logically equivalent, or the logical forms are logically equivalent. And the easiest way to check whether two statements are, or two forms are logically equivalent or not is again with the use of truth tables. So we're going to get right into a sample problem to see what we're talking about here. So we're going to show that P implies Q, or if P then Q, as well as not P or Q are logically equivalent to each other. We're going to see how these two things give you the same thing. So let's set up our truth table. We only have P and Q involved, so we're going to have 4 rows, including the 4 possible combinations of truth values that we can have. TTFF for the P column and TFTF for the Q column. Okay, we have not P involved in one of our logic forms here. So let's create the column for not P. I think it's pretty straightforward by now that we're just switching the letter that we have in the P column. T's become F's, F's become T's. So now we have FF, TT. Now we have not P or Q. We're going to take the disjunction of these 2 columns here. So a true or a false gives me a true. False or a false gives me a false. True or a true gives me a true. And then false or a true gives me a true. So there's that second to last column. And now we have the final column. The P implies Q. This is just straightforward. Do you recall the truth table for the conditional and what it does? We're working with these 2 columns. True implying a true gives me a true. True implying a false is a false. False implying a true gives me a true. And then false implying a false gives me a true. So we see that in this last column we have TFTT. Now what makes these 2 logic forms here, the not P or Q, as well as the P implies Q, what makes those logically equivalent is that they have the same truth values for every single row here. No matter what truth values we have for P and Q individually, these 2 things have the same truth values. So when that is the case, we say that those 2 things are logically equivalent. Another one here, let's show that P and not Q and the negation of P implies Q are logically equivalent. So what we're looking to see in the end is that these 2 columns here have the same truth values no matter what P and Q are doing over here on the left-hand side. So first, let's fill in that column for not Q. T's become F's, F's become T's when we're doing the negation. So FT, FT. Now we can take the conjunction of P and not Q. A true and a false gives me a false. True and a true gives me a true. A false and a false gives me a false. And then a false and a true gives me a false. The other logical form that we want to work with is not P or Q, but let's come up with the column for just P implies Q, and then the final column will take the negation of those values. So again, P implies Q, going down, true implies a true gives me a true, true implies a false gives me a false, false implies a true gives me a true, and false implies a false gives me a true. So we are now at this stage here. And now lastly, we have not P implies Q, so switch the truth values here. False, true, false, and false. So now, again, looking back at these two columns, P and not Q, as well as not P implies Q, we see that we have F and F, T and T, F and F, F and F. And thus, whatever truth values we have for P and Q here, we have the same truth values there. So we know the negation of the conditional. We know what the negation of a conditional is. Also from our previous problem, we saw what just the conditional was equal to as well. But what about some of the other logical connectors? For example, what if we take the negation of a disjunction or a conjunction? Well, to deal with that, we have these laws called De Morgan's laws. And you can verify these on your own. But the negation of P or Q is logically equivalent to not P and not Q. Also, the negation of the conjunction, or not P and Q, is logically equivalent to not P or not Q. Those three horizontal lines there, that's the symbol for is logically equivalent to. Logically equivalent to. That's just what that's saying. For example, taking those logical forms and putting it into a sentence, the negation of I am 30 years old or I drive a Nissan is I am not 30 years old and I do not drive a Nissan. So if you negate an or, it becomes an and. If you negate an and, then it becomes an or. Putting some extra emphasis and focus on the implication or the conditional statement P implies Q, there are some related statements to it that I want to talk about, and then I'm going to talk about how those statements are related to each other. If we are given a conditional statement, P implies Q, we have the inverse, the converse, and the contrapositive. The inverse is when we take the negative of P and the negative of Q separately, and we do that implication. Not P implies not Q. The converse is when we switch the places of P and Q. So the converse now becomes Q implies P. And lastly, we have the contrapositive, which is sort of doing the inverse and the converse. We're going to take the negation of P and the negation of Q separately, and then we're going to switch the places of those things. So the contrapositive is not Q implies not P. So let's just see what these things look like in terms of an actual sentence. Here is a conditional sentence. If you wear a red shirt, then you will get stopped by a cop. We're going to see what the inverse, the converse, and the contrapositive of these things are. The inverse, again, this, you wear a red shirt, and you will get stopped by a cop. Those are our simple statements P and Q. So the inverse, we take the negative of P, we take the negative of Q, and we do that conditional. So it would become, if you do not wear a red shirt, then you will not get stopped by a cop. Not P, not Q, conditional in the same order. The converse, we're just switching the places of Q and P. So this guy comes first, this guy then comes second. So the converse would be, if you get stopped by a cop, then you wear a red shirt. The contrapositive is, as we just said, a combination of the inverse and the converse. You take the negation of each of our pieces individually, and then you swap their places. So the contrapositive is going to be, if you don't get stopped by a cop, then you don't wear a red shirt. So now, how do these statements relate to each other? How does a given conditional statement, its inverse, its converse, and its contrapositive, how do those things relate to each other? And this is the last thing I want to touch on in this video. A given conditional statement and its contrapositive are logically equivalent to each other. I encourage you to verify this. Set up a truth table and check that P implies Q, as well as not Q implies not P, are logically equivalent. Check that you get the same truth values going down those two columns, no matter what combinations of truth values you have for P and Q individually. The inverse of a conditional statement and the converse of a conditional statement are logically equivalent to each other there. However, these sets of things are not equivalent to each other. Conditional and contrapositive say one thing, inverse and converse say something else, but those two sets of things are not this. But those two things that they're saying are not the same thing. So this concludes our video on logic, truth tables. We talked about tautologies, contradictions, logical equivalence of two statements, and then the inverse, the converse, and the contrapositive. In the next video, we are going to start a new chapter, and we're going to get into the different types of numbers that we encounter typically in our work with mathematics, and how those sets relate to each other. If you have any questions or comments, please be sure to reach out to me, guys. Send me emails, rocks through my window, flare signals, send up a signal with your magic wand, whatever you have to do. Otherwise, until the next video, take it easy, guys.